go over a little bit of housekeeping. So when you joined, you should see a language selection option. It should have asked you which language when you first log in. If for some reason that didn't happen, or you selected wrong, you can select it at any time during the course. So you can, where Annie's putting the cursor, at the top of the screen, select More, and then from the drop-down menu, click on Language and Speech, and then click on Interpretation Language. That'll open up a pop-out box where you can select between 5 languages, so English, Mandarin, Japanese, Korean, and Vietnamese. So you select your language, and then you can select the volume. So if you move the slider more to the right, then the interpretation, the translated voice, is going to be louder. If you move the slider to the left, then the original voice of Annie will be louder. So where it's showing in this picture seems to be just about right, but you can adjust this later on as well. We have everybody's microphones muted, and we ask that you stay muted throughout the presentation. If you have any questions, you can enter them into, there's a Q&A box at the top of the screen. So you can select that and you can enter your questions in there. It probably works best if you can enter in English. However, if you want to write them in your own language, then we have the ability to translate. Plus, we have our local staff from various countries as well that can jump in and help as well. So we're going to go right through the presentation, and we'll leave some time at the end for questions and answers. Okay, so with that, I will introduce our presenter on the next slide. Okay, and Annie's got her camera on for a little bit. So Annie Watt, she's our Senior Manager of Clinical Education for the Asia Pacific region at STERIS Corporation. She has over 25 years of global experience in decontamination, sterilization, and infection control protocols. Annie is a recognized leader in the field, a registered nurse with postgraduate certifications in perioperative and acute care nursing. Annie brings deep clinical expertise and a strong background in the medical device industry across Australia and New Zealand. She has also served as a consultant for medical manufacturers worldwide. Annie is deeply committed to improving patient outcomes. She collaborates closely with healthcare professionals to deliver education, training, and troubleshooting support, ensuring optimal results for both customers and patients. Her current role encompasses clinical education and training across Australia, New Zealand, and all of Asian markets. Annie is a frequent speaker at national and international conferences where she shares insights on infection control, decontamination, sterilization, and the implementation of relevant standards. Annie has presented at numerous professional associations, including New Zealand Sterile Supply Association, Federal and State Sterilization Research Advisory Councils of Australia, Japan Society of Medical Instrumentation, Hong Kong Infection Control Nurses Association, Malaysian Sterile Supply Association, Thailand Sterile Services Association, Indian Central Sterile Services Association, China CSSD and Nurses Association, and China Infection Control Association, as well as Singapore Infection Control Association. These just to name a few. So with that, I'd like to introduce our speaker and hand it over to Annie Watt.
Good afternoon, everybody, and thank you for joining us. As Brian said, I'm going to just turn my camera off so that we have good reception. Sometimes it's not great when we have a lot of people on the call. So I'll turn this off and we can get started with the presentation. So today we are going to talk about, as Brian mentioned, new frontier of hospital sterilisation of 3D printed devices. And we are going to cover just three objectives. Identify what 3D printing of medical devices actually entails. Identify the challenges of processing 3D printed devices, and identify steps in processing of 3D printed devices. Before we actually dive deep into the presentation, I have a video which I would like to show you all, just so you get an understanding of what 3D printing of medical devices entails. And this is from a hospital in the US.
I'm Brad Strong, one of the otolaryngology head and neck surgeons here at UC Davis Medical Center. When we think about complex surgeries many years ago, there was a lot of uncertainty. What was it going to look like when we got in there? How were we going to manipulate the bony segments? What kind of hardware were we going to apply once we were in the operating room? 3D printing allows us to do this planning, to hold the patient's skull, see the injuries prior to going into the operating room, and give the patient the best chance possible to have a surgical outcome without any changes in their facial appearance. So we take the patient's CT scan and we input it into our planning software. We generate a virtual model that we want to then print. The printer itself prints in layers and then builds layer by layer until we have the precise final structure that we are looking to sterilize and bring into the operating room. And we can use these sterilized models to bend implants in a very precise nature that will reconstruct the patient's pre-injury anatomy with such precision that we can't do it without this type of a model. As we look into the future for 3D printing, it's very exciting. We may be able to print a kidney or a liver, skin, bone, and actual implants that will stay within the patient. These things are on the horizon and potentially not that far in the future, and UC Davis is trying to stay on that cutting edge. This is a very exciting time, and we hope to be leading those new discoveries that are going to be happening in the very near future.
So that's just a quick understanding of what 3D printing for the operating room can actually look like. But what actually is 3D printing? Well, it is a process that involves the creation of a three-dimensional physical object from a digital 3D file. And it's also called additive manufacturing, which refers to any process where a product is created by fusing several layers of material to create a single three-dimensional object. But for this presentation, we are going to refer to this as 3D printing. So we have 3D printing, and we have it in many applications in healthcare, and manufacturers use 3D printing applications basically to create and modify device prototypes during research and development of new medical devices or treatments. And some manufacturers use 3D printing processes to make medical devices that are sold to healthcare facilities for patient use. For example, here you can see that we have got some implants here, and these appear to be made of a sintered metal. So this 3D printing allows complex medical devices to be made specifically for the patient. So these are implantable devices like hip implants that require really complex geometries or enhanced designs for maximum integration with the patient's anatomy. We also can create 3D printed medical devices which are specific devices that improve the fit and ultimately lead to a greater patient satisfaction with things like form-fitting splints, prosthetics, dental alignment devices, etc. So if we have these types of devices, as we print them, these are specifically made for the patient, so they have a specific improved fit and design. The last category that is relevant to healthcare are 3D printed devices that include patient-specific devices that are made at point of care. And these are things such as surgical guides and anatomical models. And you can see here, this is an anatomical model of part of a spine. Patient-specific surgical guides are typically cutting and drilling jigs that are used within a procedure. They can be osteotomy guides, spinal surgical guides, and dental implant guides, and they guide the surgeon to make exactly precise drill places, attaching of screws, all things that are relevant to having the actual device when it is implanted in exactly the place that it is required. Anatomical models are physical representations of the patient's anatomical features, and they help surgeons plan for complex surgical procedures as well as educate patients about their condition and treatment plans. And we see anatomical models used in conjunction with surgical guides on many occasions. Oops, sorry, clicked too far. The anatomical models actually provide many advantages for surgeries, and they cover a lot of the complexities. So improved surgical planning, including the selection of surgical approaches and tools, is one area, and this helps reduce the surgical time and the amount of time that the patient is sedated, which leads to basically better outcomes for the patient, reduced recovery time, and greater patient satisfaction while saving the facility some money. Anatomical models enhance communication across medical disciplinaries, and during surgery preparation, they all work together. And these teams can anticipate situations that help reduce surgical complications, which ultimately is good for the patient. The anatomical models can be used during surgery to verify assumptions and confirm surgical manipulations of the procedural site. And they can also help surgeons teach the patient about their condition and the procedures that they are going to take to improve the outcome for the patient. So the patient can actually see the anatomical model, and it can be explained by the surgeon as to what they are going to do to improve the outcome for the patient. So you might ask, why haven't we heard about these? I'm sure many people have heard about 3D printing in healthcare, but some people haven't. And who does this? How often? And where do we do this? So you will see that today over 500 healthcare facilities are 3D printing point of care medical devices. And these point of care, when I say point of care, I mean they are printed at the hospital. So many of the large hospitals actually print these 3D devices as they can actually utilize these types of devices to ensure that the patient is getting the correct device implanted into their body. You will see that pediatric hospitals, and we have a lot of pediatric hospitals that use these types of devices for children with all types of issues. As you saw on one of the screens prior, we have patient-specific devices to improve fit with hands, legs, all sorts of areas. So these at pediatric hospitals are extremely popular. We also have teaching hospitals, and the teaching hospitals, the advantage of this is that when surgeons are teaching new young university surgeons or medical students, they actually can show some of the issues by using these 3D printed devices, and then they can show the outcome that they received by actually having these 3D printed devices in the operating room at the time. And we've seen lots of advantages in orthopedic, prosthetics, pediatric, oncological and orthodontic specialties. But honestly, this day and age, we are seeing 3D printed devices being used in all types of surgery, including spinal, cardiac, etc. And as that video explained, we are looking into the future of doing 3D printed devices that may be more organ related, skin related, artery related, venous return related, all of those sorts of things. So this is quite a forefront of technology. So 3D printed medical device workflow, and how do we actually print these medical devices when we have them required? The workflow is divided into 4 processes, and the first step is to capture the image of the patient. So in hospitals, we have many imaging devices to capture patient-specific imagery. We can use CT scans, MRI, X-ray, and even sonograms have been used in the past. The images are then converted into a 3D printable file, which is called segmentation. And there is special software that is used to perform this task. The resulting 3D printable file from the segmentation area is then used by the 3D printer to print the medical device. After the printing is complete and all steps have been followed to clean and finish the 3D printed medical device, the device is then prepared for patient use. The necessary activities to prepare the device for patient use will be dependent upon the type of medical device and its use. For example, medical devices that will be used in surgical procedures, of course, must undergo the appropriate cleaning and sterilisation procedures before it is used. And healthcare facilities should actually map the entire workflow and develop policies and procedures appropriate for each process within the workflow. And this will ensure appropriate quality practices are in place to make 3D printed medical devices. So what is needed? In these hospitals these days, if you are going to 3D print medical devices, you need to have a cross-functional implementation team that will ensure that all aspects of the workflow are captured and documented. The team should include surgeons, radiologists, imaging staff, 3D printer software specialists, infection prevention, risk management, and if sterile processing leadership is involved, that will be when the device is required to be cleaned and sterilised prior to patient use. The radiology department of the hospital bears the responsibility of image capture, segmentation, and actually the 3D printing. And this includes obtaining the image files, converting the image files into a compatible 3D print file, selecting the best printer and materials for the medical device's application, and the final post-processing steps, which may remove printing residues, support materials, and then completing the curing process, which may be leaving the 3D printed device in under an ultrasonic light for a period of time. The exact post-processing steps are defined by the 3D printer manufacturer and the materials used to 3D print the medical device. So as we have seen with lots of hospitals, as this becomes a larger and larger area for the hospital, we have seen that the 3D printing is removed from the radiography department and they actually find a space that they can actually dedicate to the 3D printing as it grows. There are lots of different 3D printing techniques, and I'll just run through these very quickly. There is fused deposition modelling, where a strand of material is heated and deposited in layers to create a 3D printed object. We have stereolithography apparatus, which is a curable photopolymer, typically liquid, a liquid resin. It's hardened by applying focused light or UV light. As I said before, when we are curing these 3D printed devices, they are often popped into UV light to cure them properly. Selective laser sintering is a laser is used to fuse the thermoplastic powder to build parts that are needed for the actual operation. Direct metal laser sintering creates objects by fusing a metal powder with a laser. Material jetting, droplets of material are selectively deposited and cured on a build plate, and electronic beam melting. I think a lot of people have heard of this. An electronic beam is used to fuse metal powder together to build parts. So these are just a few of the options available to 3D print medical devices. And the surgeon, radiologist, software specialist, and printer vendor will work together to select the printing process and materials best suited for the facility's needs and for the patient outcome. So what are the sterilisation, the CSSD processing responsibilities? So the SPD or CSSD are responsible to clean, rinse, package and sterilise the 3D printed medical devices that require sterilisation prior to use. The leadership team is responsible for training and demonstrating competency of sterile processing staff. So those staff that are competent may then be assigned to these tasks. The leadership team in the CSSD must also ensure that the staffing, equipment and consumable inventories can be met and that for the demand of the surgical and radiology teams. So far, so good. It's like any other process that we do in the CSSD. So where do the instructions for use come from? The manufacturers. So the manufacturers of medical devices design the device, test the device, and obtain clearance to sell the device. As part of this process, instructions for use are written by the manufacturer that detail the cleaning and sterilisation instructions to follow. The manufacturer also sources the materials and the equipment that will be used to make the device. And the device can be made in the hospital or it can be made in the manufacturing facility. When the hospital buys or borrows the device from the manufacturer then must provide an IFU used by the sterile processing team to develop and write policies and procedures followed when processing these 3D printed devices. Some of the 3D printed medical devices follow this same process and have a manufacturer IFU as well. And we will all know that we have loan sets that come into the CSSD that are 3D printed devices, and they come from the manufacturer and they have an IFU. However, the majority of 3D printed medical devices that are 3D printed at point of care in the hospital environment will not have a manufacturer provided cleaning and sterilisation instructions for use. And this is the reason why. When healthcare facilities choose to 3D print medical devices at point of care, the radiology team chooses what they will be making based on a discussion with the surgeon on the surgical plan. They determine the design of the medical device through imaging and segmentation software. The surgeons may provide guidance on the material and the device's quality expectations. So the surgeon might say that they would like it made of resin or they would like it made of metal, depending on what they would like. Radiology, working with the surgeons, source the material. It will be made of, that's whatever it is, whether it is a resin, a plastic, a polymer or a metal. So they will work with the surgeons and they will source the material it will be made of and the printer that will make the desired 3D printed medical device. So basically, the hospital is the manufacturer of the 3D printed medical device. They have sourced the printer, they have sourced the material, and they now will print that 3D medical device in the radiology department. For this reason, there are no manufacturer instructions because the hospital is now the manufacturer. The hospital, or rather the cross-functional implementation team, would now need to develop the instructions for use and for reprocessing. FDA apparently is currently writing guidance on how hospital 3D printing will be regulated. However, I don't have any update on that at the moment. So, sterile processing challenges from 3D printed medical devices can be quite hard. And the workflow actually creates three major challenges for the CSSD. Devices are patient specific, and as such, they are very unique. And this means processing instructions for one device may not work for different 3D printed devices. And the reason being is that some of these devices may not have any lumens, whereas other devices have lumens. These are the things that must be considered. If we don't have a vendor, we do not have an IFU. And add to this, there is little or no guidance documents or standards that detail processing 3D printed medical devices. All of this leads to the CSD needing to create processing instructions. So everybody needs to work together. The CSSD leadership are not expected to create processing instructions. They will be part of a cross-functional 3D printed medical device implementation team who will work together and develop and validate the appropriate cleaning, rinsing, drying, packaging, and sterilisation processes to prepare the 3D printed point of care medical device for patient use. So how do we navigate this? Well, we use the 3D cross-functional, the 3D printed medical device cross-functional implementation team along with our quality management system. So healthcare facilities should actually turn to the ISO standard 13485, which is medical devices quality management systems, and shore up their existing quality management systems for point of care 3D printed medical devices. The standard actually details the requirements of a quality management system responsible for the manufacturer of medical devices. So now that the hospital is the manufacturer of medical devices, they need to look at the quality management system. Many healthcare facilities will require modification. So they will need to look at their risk management, their design development, specifications, design validation, quality control, and manufacturing control. And ultimately, the cross-functional 3D printed medical device implementation team will work with affected departments to ensure that we have development and compliance with the quality system management activities necessary for point of care 3D printed medical devices. And within the recommendations will be the requirement to develop and test a process to prepare 3D printed medical devices for patient use. So for sterile processing, it will support processing decisions and lead to a robust quality management and quality control system. It's a lot of work, but it is what is required if you are going to do what we say point of care 3D printing. So once the quality management system has been shored up, it's time to develop processing instructions that work for both the CSSD and the point of care 3D printed medical device. So we have processing steps for patient use. And when we think of sterilisation, we envisage the three-step process with each step having multiple tasks. Cleaning is the first step in the processing of medical devices for patient use. And this should not be confused with post-processing of the 3D printed medical device. So remember I said after the device is manufactured in or printed, it needs to be cleaned and then it needs to be finished correctly and sometimes cured with UV light. So that is what we call post-processing and is not to be confused with the cleaning process. So cleaning is performed in the CSSD to remove contaminants and reduce microbial contamination that the 3D printed medical device may have been exposed to during the actual process of manufacturing. After the device is cleaned, rinsed and dried, it must be packaged for sterilisation, just like all other products or devices in the CSSD. The device, along with a chemical indicator, is placed within a barrier system in preparation for sterilisation. Typical barrier systems used in CSSD include sterilisation wrap, sterilisation pouches and container systems. And the last step is sterilisation. And the most common sterilisation applications within healthcare facilities include steam sterilisation and vapour hydrogen peroxide sterilisation. The cross-functional implementation team must work together to identify the process, the equipment, and the consumables necessary for each step in the process. And once identified, each step must be validated to ensure that the specifications are met and the facility can reproduce those specifications every time they have to reprocess a 3D printed medical device. So, process validation. So in cleaning, basically in cleaning, we have to demonstrate that the cleaning process can remove the expected contamination on the device without leaving cleaning, chemistry, residuals, or endotoxins. The process must also be compatible with the material that the 3D printed device is made of. The process should consider whether we are going to have a manual or an automated process. Are we going to just wash the device in the sink, or are we going to place it in the washer disinfector or the ultrasonic machine? We need to ensure that medical grade cleaning chemistries are used. These cleaning chemistries have been designed and tested for surgical instrumentation, and they rinse freely from device materials. So using dishwashing detergent or things like that are not what we require for cleaning of surgical instruments and 3D printed devices. We need to be very, very mindful of material compatibility and that what we are washing is compatible with the material that we are using for the 3D printed device. We must be very, very careful of our water quality required for cleaning and rinsing of medical devices. Water impurities can have very bad effects on materials and can interfere with cleaning and sterilisation. So consider using utility water for intermediate rinses and critical water for final rinses. The drying process should also be defined. How will the device be dried? Is it air dried? Is it a drying cabinet? Is it part of the washer disinfector cycle? We have to have considerations for all of these: the temperature, the device design, the material of construction, and the total time required to dry the device. And that's just for cleaning. If we look at the process validation for sterilisation, sterilisation validation requires three things to be successful. It must prove sterile efficacy for the sterilisation cycle, biocompatibility of the 3D printed medical device, and material compatibility. So in simplest terms, sterile efficacy testing starts with medical devices that are inoculated with bacterial spores and then shows that the spores have been killed or inactivated within a specified exposure time of a defined sterilisation cycle, whether that be steam or vapour hydrogen peroxide. Biocompatibility testing shows that materials or medical devices will not cause an undesirable result both locally and systematically in the patient when used as intended. And the material compatibility testing proves that sterilisation process does not significantly alter the 3D printed medical device, making it unusable or unstable for its intended use. So we have to consider other things. The sterilisation process should identify the sterilisation modality and cycle parameters. So not everything that things that we 3D print, we cannot just place into a steam sterilizer or a vapour hydrogen peroxide sterilizer and think that that will be okay. There are lots of things that we need to consider with the sterilisation modality. It's important to choose a cycle that is validated for the sterilisers in the department, and using off-label sterilisation parameters could require additional testing And if you use off-label sterilisation parameters, you could also cause issues with the patient. The load configuration should also be identified. How many devices will be sterilised at one time? What is the number of devices to be sterilised? What is the weight of the load? All of these things must be considered. Also, the sterilisation process should identify the sterilisation barrier systems and their accessories. So the sterilisation pouch materials and size, the wrap, the weight, the tray that is going to be used to hold the device, the container systems and the filter models used, and each sterilisation process kills and inactivates bacterial spores differently. So it may be necessary to validate all of the consumables that you use when you are validating these cycles of sterilisation for 3D printed medical devices. An important consideration when selecting or developing a sterilisation cycle is to use an existing steriliser manufacturer's programmed sterilisation cycle. So if we've already got a cycle that is programmed and validated, we should use that. Using these cycles gives a few advantages. The first is that the accessories necessary for the sterilisation cycle have already been validated and the FDA cleared for that cycle. Sterilisation wraps, pouches, trays and other barrier systems will have been developed and validated for the process, and that reduces the quantity of necessary validation testing for the 3D printed medical devices. So if you've got a vapor hydrogen peroxide sterilizer that can already has a cycle that is already validated to reprocess 3D printed medical devices, then that's half of your problem solved. Using validated sterilizer cycles also gives assurance of the sterilizer's performance. The sterilizer manufacturer would be able to provide a preventative maintenance plan and cycle performance confidence. And remember that though the sterilizer may have been validated and 510 cleared, the clearance may not include 3D printed medical devices. In fact, most sterilisation options available to sterile processing do not have clearance requiring extensive sterilisation validation testing to be done. So that means that we don't have, there's only a very, very few, or one in actual fact, that can do this. So at the moment, you're looking at sterilising 3D printed medical devices, and you don't really know how to do this. So it is a bit panicky. It does give anxiety to a lot of people. However, there are experts that are standing by to help, and many contract laboratories offer cleaning and sterilisation validation services. They know hospitals are not experts at this type of validation, and these people are, which is why they provide this service. It's probably best to look at a reputable laboratory that is experienced in cleaning and sterilisation validations, as they'll be able to help walk through the 3D printed medical device implementation team process. So whatever the implementation team need to do, these people will walk you through that process. And they can also write the test protocols and perform the validation testing if that is necessary as well. I did say that most sterilisers are not cleared for 3D printed medical devices, to sterilise 3D printed medical devices. There is one steriliser model on the market that has received clearance to sterilise 3D printed surgical guides and anatomical models, not implants. Using FDA cleared sterilisation for point of care 3D printed surgical guides and anatomical models that meet the device specification of the sterilizer cycles has significant benefits. Since the cycle is validated and FDA cleared and issued with 510K certification, 3D printed guides and models that meet its specifications would not require sterilisation validations, and that would save the healthcare facility time and money. The sterilizer cycle would have FDA cleared accessories for the cycle and 3D printed guides and models. So you wouldn't have to revalidate your accessories. The manufacturer would also have an appropriate preventative maintenance plan and confirm sterilizer performance of the cycle. In some cases, the cleaning recommendations may also be available, which would eliminate the need for cleaning validations. However, the claims are specific. The 3D printed medical device implementation team would need to confirm that the 3D printed devices would fall within the cleared specifications. So if you have a 3D printed device that does not conform or fall into what is cleared for that particular sterilizer, you cannot place it in the sterilizer. So once the cross-functional implementation team has developed and validated the processing steps for the point of care 3D printed medical devices, the workflow within the sterile processing department becomes routine. It's normal things like we normally do. We transport the 3D printed medical device to the CSSD. The device should be protected while it is transported so that we don't have any damage or it doesn't become contaminated with environmental microbes. Once the CSSD receive the device, the cross-functional implementation team should consider where the device will be received and what information should be delivered with the device. So we need to actually make sure that the trained staff who have demonstrated competency know exactly what is coming into the department, what needs to be cleaned, and what information is with it. Once we clean it, we assemble it, it is checked. It has to actually be checked so that there is nothing wrong with the device, there is nothing broken or deformed, and then we place it into the tray or the packaging material with a chemical indicator, and using the validated sterilization cycle parameters, we sterilize that device. If you use a biological indicator to release it from the load, then you must actually use that biological indicator and wait for the result before you release the device from the load. There is a concern about patient identification and traceability because the point of care 3D printed medical devices are patient specific, and it's critical that the device gets on the right case cart for the right patient. So patient identification is necessary on the device prior to being received in the CSSD, and there are many ways that this information can be transferred to the CSSD at time of receipt. And we all know we have tracking systems, traceability systems. Whatever your track and trace is within the CSSD, it has to start from the radiology department at point of care, and that information comes down to the CSSD and leaves with the device. Now, that device can be actually stored in sterile stock. It can be sent back to the patient, or it can be sent to the radiology department to be stored there. But the patient identification and traceability is a key element so that that particular device will be implanted or, will be used with that particular patient, as they are unique. There are other considerations that we have to remember as well. Like all devices, we can get cross-contamination, and it is an important consideration when we are developing the workflow for these things. We also need to inspect the 3D printed device before we assemble and pack it in case it has damage to the device. We need to review the quality assurance activities to ensure that these activities are suitable for the 3D printed medical devices processed by the CSSD. We have to manage all non-conformities. So if the 3D printed device is damaged, what if the sterilization cycle fails or aborts? What do we do then? And we have to document all non-conformities. We also have to have a plan of recall policies and procedures so that we, if there is an issue with the 3D printed device at point of care, that we can actually draw on these recall policies and procedures. So the future of personalised and patient-specific medical devices has become reality with point-of-care 3D printed medical devices. Though there may be processing challenges, the benefits to patient outcomes far outweighs the activities we do to overcome these challenges. So I did mention to you that I would quickly give you a little bit of information of the actual manufacturer that can sterilise 3D printed surgical guides and anatomical models. So STERIS has introduced the specialty cycle for the vPro Max 2 sterilizer. And these cycles are specific only with the registered manufacturers that we work with. STERIS has acquired FDA 510K clearance, and they remain the only FDA cleared vapor hydrogen peroxide sterilisation manufacturer that has these specialty cycles. The specialty cycles are called D, E and F, and I will explain why in a minute. And the specialty cycles are validated with manufacturers who are global manufacturers, Formlabs and STERIS. Formlabs have what we call a biomed amber resin or a clear resin, and they use cycle F and cycle D in the specialty cycle. And STERIS, whatever they have, they just use cycle E with the testing that was performed. These are validated materials, and they are new materials that Formlabs and STERIS have actually designed that can be reprocessed through the STERIS vPro Max 2 vapor hydrogen peroxide sterilizer. They are single-use devices, and they require very long aeration times. So the specialty cycles, for cycle D, it is 8 hours. For cycle E, it is 16 hours. And for cycle F, it is 21 hours. And I know you're all going, why is this so long? The sterilant and the sterilisation cycle itself is very much like the sterilisation cycle we use for our vapor hydrogen peroxide machines. And whether that be a short cycle or a 50-minute cycle, it doesn't matter. Those cycles are, the sterilant is the same type of process. Where the extra hours come from is aeration, where the vacuum is drawn and pulled out of the chamber so that we remove any residual vapor hydrogen peroxide from these porous devices. This is the testing that was done with Formlabs and STERIS was all submitted to the FDA for their clearance and their 510K certification. So that's why the cycles are so long. It's about aerating the devices so that there is no vapor hydrogen peroxide left in the device which could damage the patient. The cycle claims, basically, there are limits on weight, which is 2.3 kgs of device in the chamber. And whether you are doing cycle D, E or F, you'll see that there are lumen dimensions, lumen diameters, inner diameters, and length of the devices. So this information is available for us to provide to you. If you need this information, we are very, very happy to provide the information. If you scan the QR code here, it will give you further information about how to sterilise 3D printed materials in the vPro Max 2 low temperature vapor hydrogen peroxide sterilisation system. I have references here. If you would like, I can actually provide these references for you. I'd like to thank you for listening to the presentation. If you would like to contact me, you can scan the QR code here and you'll have my details, my email address, and my phone number. If you would like to contact me for more information, please do so. I do know that we have had we've had many questions about the vapor hydrogen peroxide system and duodenoscopes. So I'm just going to quickly hand over to Brian Ainge, who's our marketing manager, and he is going to give you a quick update on that information.
Thank you once again.
Thank you, Annie. Okay, so we've had questions sent before the presentation. And we've had a lot of questions about our new GI claim as well. So I just want to address that here. So yes, it's true. We can now support the sterilization of certain duodenoscopes and gastroscopes. And using our existing flexible cycle on the vPro Max 2 sterilizer. So nothing needs to be added, nothing needs to be changed. But before you go down this road, we do ask that you, if you have a question on any specific devices, that you reach out to your local sales rep from STERIS or clinical specialists. We will try and address this in the future with another webinar. And basically, I mean, just because we can sterilize some of these scopes using something like vPro doesn't mean that's always, there might be other options that make more sense for certain hospitals, such as liquid chemical sterilization. So there's quite a few questions around this, and we'll address it all in a future webinar. But in the meantime, if anybody does have any questions on this, just reach out to your local rep or use any of the emails on this webinar as well. Okay, so outside of our extended GI claims, there have been some other questions that were sent in earlier that we will take a look at. And if anyone else has questions, please do type them into the chat box or the Q&A box that you see at the top of the screen. So for now, I'll start with some of the ones that were sent in ahead of time. Is that good, Annie?
Oh, good. Let's go. Yes.
Perfect. All right. Okay. Are there any other vaporized hydrogen peroxide sterilizers that are cleared to reprocess these devices?
No.
Meaning
STERIS. Yeah, no. STERIS are the only low temp vapor hydrogen peroxide sterilizer that is cleared by the FDA with 510K to to process 3D printed medical devices in the specialty cycle. To date, nobody else with a low temperature sterilizer has these claims.
Great. And then the next question, and sorry, these are, I don't know which sessions these people joined, so we're addressing these questions in both sessions.
Okay.
Someone did ask if they already have a vPro Max 2, but they ordered it before these specialty cycles were available. How can they address these devices? Is there any way for them to be able to address these devices, or is it only available on newly ordered vPro Max 2 units?
No, this is a software update to add the specialty cycle to the vPro Max 2. So if you have purchased a vPro Max 2 for your department and you are wanting to reprocess the 3D medical devices that I showed you from the manufacturers on the list, then you may speak to your STERIS distributor or your STERIS direct contact, and they will be able to provide you with information of how you can update and have the specialty cycle added to your machine.
Yeah. Someone asked, can I sterilize all of my 3D printed devices through vPro Max 2?
No, you can only sterilize what has been validated. So in the special cycle, which is why I showed you, Formlabs and Stratasys are the two manufacturers, global manufacturers, that STERIS have worked with. They are two of the largest manufacturers of 3D printing materials. If anybody would like their contact details, if you would like to, I'll just go back. If you would like their contact details, please scan the QR code and I can provide you with the Asia Pacific contact details for Formlabs and Stratasys. And when you have that information, you may then be able to provide that to your radiography department or your surgeon, and they can work with Formlabs and STERIS. And if you have a vPro Max 2, it would be very worthwhile for you to do that so that you don't have to revalidate all of the things that you are trying to process through your sterilizer.
Okay, and then someone else asked, why can I not use any of my standard cycles on any vaporized hydrogen peroxide sterilizer? For example, whichever sterilizer we're using, can we not just use the longest cycle available?
No, you can't, unfortunately, because of the aeration required. So all of the testing that was done, you saw in the program that the cycles are 8 hours, 12 hours, and 21 hours, or what I can't remember. But they are extremely long. And the reason that they are so long is we must remove all vapor hydrogen peroxide from the device before it is used on a patient. So if you are placing a device that is full of vapor hydrogen peroxide on a patient to actually do as a surgical guide or as an anatomical model to see how it fits or whatever, you will then expose that patient to hydrogen peroxide. So the idea is that we don't want you or the surgeon or anybody else or the patient exposed to any vapor hydrogen peroxide residuals, which is why there is such a long aeration time. So no, you cannot use standard cycles. They are not validated for 3D printed devices.
Okay. If the material used for 3D printing is compatible with vPro Max 2, does that mean any such material can be sterilized?
No, you can only use those items in accordance with the FDA and testing. You can only use what has been validated and tested and submitted to the FDA. If that material may be the same, but we don't know if it is exactly the same. It may be a resin, but there could be other things in that resin that we cannot be sure of. Also, the device, the manufacturers, Formlabs and STERIS also had to go through this impeccable testing that is a requirement of the FDA. So no, even if it's made of the same material, you cannot use the specialty cycle. It has to be validated by and 510K approved by the FDA.
Okay, thank you. There's another one that was emailed in from Japan. Since many 3D printed products are porous, why is it that within VHP sterilization systems, only vPro Max 2 is able to achieve sterilization?
Well, I would presume that's because STERIS have been the only company that actually have done the testing. I'm not saying that other vapor hydrogen peroxide machines can't do it, but they have no FDA or 510K certification to prove that they can. So if you want to go out there and place a 3D printed device in another vapor hydrogen peroxide machine that has no testing and no clearance, then you as the hospital will be responsible for any damage that you cause to the patient. So I'm not saying that they can't do it, but they have not submitted anything to the FDA. So at the moment, there is only one machine, which is the vPro Max 2, which has been proven with their specialty cycles to be able to reprocess or process 3D printed medical devices that are manufactured. The materials and the printer come from Formlabs and STERIS.
Okay, thank you. And then Julia asks, any update on the FDA approval for specialty cycles A, B, and C?
Not yet, Julia. I'm not sure why they went with those cycles. You would have thought that they would have done A, B, C first. However, I am speaking with the R&D team, and they are continuing to test. So I would have to say, watch this space.
Okay. And then the last one I had sent in, is asking, have there been any incidents or close calls when it comes to using incorrect cycles to sterilize these devices?
Not with the specialty cycle on the VProMax 2. We have had no issues when our customers use that cycle, and no problems with surgeons or patients. I do know that there are hospitals out there that are reprocessing 3D printed devices in any vapor hydrogen peroxide machine. This is very dangerous for the patient. So I do know that there are hospitals that are reprocessing implantable devices as well as surgical guides and anatomical models. If you are doing that, I suggest that you stop immediately. The damage that you can do to the patient can be irreparable. The other thing is that there was one complaint in a hospital in Asia where the device actually broke, it cracked, because it was sterilized in a steam sterilizer and it became brittle. Also, there was one in a vapor hydrogen peroxide machine as well that became brittle and broke. And the vapor hydrogen peroxide machine had no clearance to actually use it to process 3D printed devices, and the material used that went through the steam sterilizer was not suitable for steam sterilization. So please, if you are doing or processing things, point of care, 3D medical devices, 3D printed medical devices, please make sure you are only using a validated 510K FDA approved cycle, because you can cause some serious damage to patients if you are going outside of those squares.
Okay, thank you, Annie. There is one that just came through from Tyson asking if the amount of hydrogen peroxide used in these specialty cycles is any different than the other cycles.
No, it's the same amount of sterilant used as like if we didn't have the long aeration times because of these devices, it wouldn't be an issue because the cycle would be very similar to the standard cycles that we have on the VProMax. But it's the aeration. So the sterilization time is the same with the 4 pulses. And then, so exposure time is the same. It's just the aeration time, as that machine pulls the vacuum all the time to pull out vapor hydrogen peroxide from the device, which is what we call aeration time.
Perfect. And I think that is it. Does anyone else?
Okay.
Anyone else has questions? You can probably type them in for a little while longer on this thread, and we could probably answer them or email any questions in as well. Thank you so much, Annie, for this presentation.
My pleasure.
Very
Thank you,
insightful.
everybody, for joining.
And yes, thank you, everyone, for joining, and be on the lookout for the next webinar.
Okay. Thank you very much.
Great. Thank you.
Bye-bye.